In the last few videos, we've been talking about passive neuronal membranes, and just recently I've introduced the idea that you can inject a current directly into a cell or neuron and directly affect membrane potential. Specifically, I derived this expression here, which looks very similar to the first membrane equation we looked at, except that the steady-state voltage is now described by this expression, which is dependent on the amount of injected current. So the first thing I want to look at in this video is what determines the steady-state voltage and how does the steady-state voltage change for different levels of injected current. And this is actually a pretty simple graph. I'm going to plot my dependent variable on the y-axis. The dependent variable is the steady-state voltage, and the independent variable is going to be the injected current, or INJ. So essentially, if I'm in the lab, I'm controlling the amount of electrical current that I'm passing through this electrode, and therefore, by convention, you tend to draw the independent or controlled variable on the x-axis and the response variable or dependent variable on the y. So if the response variable is just the steady-state voltage, you can see it's just a simple y equals mx plus b equation, where the y-intercept is E, which, if you remember, is the resting membrane potential, or the electrical potential that is set by the sodium-potassium pump and potassium leak channels and other electrical properties of the cell that tend to set the resting membrane potential. The slope of the line is R, which is the resistance of just channels that are constantly open, and again, the independent variable is just the amount of injected. So if I plot this onto this graph, the resting membrane potential is usually negative, something like negative 60. So let's say this is E here, and you can't have a negative resistance. Resistance always has to be positive, so this line is going to be a positive line. And you might ask, okay, so why did I choose to draw that line? I could have just as easily drawn a line that looks like this. Well, remember that the resistance sets the slope of the line. So here, the resistance of this green example is larger than the resistance of this yellow example. So this is just, quick conceptual understanding of the relationship between the amount of current you're injecting and the resistance. And, this might seem a little basic to you, and you might wonder why I'm going over this. The reason I'm going over this is because if you're actually working with experimental neurons, you don't know what the value of R is to begin with. If we're just thinking about this mathematically, you can just pick any value you want. But if you're working with an actual biological neuron, you don't know what R is, or the input resistance. So you can empirically measure what the input resistance is by manipulating the amount of injected current and then measuring what the steady-state voltage is for that level of injected current. And again, neurons with a higher input resistance are going to respond more sensitively to changes in the amount of injected current. So this leads us into the second thing I wanted to talk about in this video. Specifically, I want to talk about what happens over time as you begin to inject a neuron with some positive current. So I'm going to plot time on the horizontal axis here, and I'm going to plot a couple of things. The first is I'm going to plot a current step. So this is a relatively simple, this is flat, relatively simple perturbation that you could give to a cell. So we'll say at the beginning here of the experiment, you're not injecting any current. Then at some point you flip a switch and you begin to pass current into the neuron, and you keep that same amount of current for some long period of time. And then you flip the switch and turn it off, and then you keep current back at 0 after that. So that's the perturbation, and how is the neuron going to respond to this perturbation? Well, we know that the steady-state voltage of the neuron is just simply linearly dependent on the amount of current that you're injecting. And it's positively related to that. So if we plotted the steady-state voltage, let's see how I can do this. The steady-state voltage I'm going to plot in a dashed line, and it's going to resemble the basic shape of the injected current line. And it's just being scaled by the resistance, which is just some value here. I'm just drawing a simple schematic example, not getting into quantitative details. But if this dashed line is the steady state voltage, what does the actual voltage look like? So I'm going to draw the actual voltage in blue, sort of overlaying this trace. And at the beginning, the voltage is going to be at steady state, because let's say at the beginning of the experiment you weren't doing anything funny, you weren't injecting current or anything into the cell, so it starts at steady state. And then you flip the switch, and when you flip the switch, what's going to happen to the voltage? Well, we know the voltage is going to approach this dotted line, but it can't approach it instantaneously because of the time constant in this equation. And we've already sort of seen what happens in this situation before when we were talking about the phosphorylation, dephosphorylation of proteins, or activation, inactivation of proteins. So what exactly is the voltage going to do? Well, it's going to exponentially approach the steady state. So it's going to sort of look something a little bit like this. And let's say you're leaving it on long enough so that it perfectly reaches steady state, or essentially reaches it for all intents and purposes. Okay, and then when you flip the switch off, what's going to happen? Well, again, the voltage is going to try to reach back to its steady state value, but it can't do it instantaneously. And you just have a simple exponential decay. And if I can draw this correctly, the time course should be the same for the fall time and the rise time, because the time constant of the membrane is constant. So in this case, the blue curve would be V, and this just gives you some simple intuition about how the voltage tries to follow the steady state voltage, but it can't do it instantaneously. And in the next video, I'm going to talk about this a little bit more in depth and consider what happens if we have different current injection protocols. So I'll just give you a quick example over here. So in this video, we did a simple step current, but there's no reason why we couldn't inject a sinusoidal current, or a white noise current, or some sort of noisy current. And these different protocols, sort of get at different things and different properties of what the neuronal membrane actually is doing and how it responds to inputs. And luckily, the system here that we were talking about is simple enough that we can actually answer and solve for what the membrane potential is going to be for all these complicated inputs exactly. And I'll start talking about that in the next video. Thanks.